Have you ever wondered, what is the smallest thing in the universe? Welcome to the quirky world of particle physics. Sure, we have the molecule and the atom, but atoms are made up of neutrons, electrons, and protons. Sure, that's as small as it gets, right? Wrong.
Well, not quite. Electrons are indivisible, and scientists once thought protons and neutrons were too. But if we keep zooming in, we find that they're actually made up of another group of fundamental particles called quarks, each with fractional charges.
This group excludes electrons, but don't worry, they're part of their own family of particles called leptons. Along with leptons and bosons, the 6 flavors of quark help make up what is called the Standard Model of Elementary Particles, the periodic table of elements for particle physics.
Whoa, that's a lot of particles.
It sure is, but 60 years ago, when scientists first started smashing particles together, there were a ton more subatomic particles, each with their own names, rules, and classifications, which changed often, and without anyone really knowing how they related to each other.
It was a mess.
That was until 1961, when Mann grouped them into the eightfold way, predicting another particle in the process. Him and George Zweig independently found a trend. It looked like all of them could be disassembled into 3 types of tiny, indivisible pieces: the up, down, and strange quarks.
When scientists found that electrons would scatter off of neutrons when fired at very high energies, they figured that something inside neutrons had to be charged, thus confirming their existence, or the existence of something similar.
Then, the theorized trump quark was discovered, followed by the top and bottom quarks.
Now, quarks each have 5 distinct properties.
Flavor, mass, spin, electromagnetic charge, and color charge. You heard right, color. This color is a special charge similar to electromagnetic charge. It comes in 3 different types and is named after the 3 primary colors of light for convenience: red, green, and blue. But like flavors, this could easily be replaced with something else, like rock, paper, and scissors. And, like other particles, these quarks also have anti-equivalents, like Spider-Man. With the help of another color-charged photon-like particle, the gluon, quarks can change color, or even pop in and out of existence. This color change can happen so long as total color charge is conserved, just like electric charges, and composite particles stay color neutral. So, quarks can't exist alone. Similar to magnetic north and south poles. If you try to pull them apart, we eventually get a new quark-antiquark pair through a process called hadronization. Simple color combinations of quarks exist as color-anticolor pairs, or as groups of all 3 colors or anticolors. Together, these 2 amigos keep the nuclei from exploding by carrying a fundamental force of physics, the strong force. Moreover, with the help of the W boson and another fundamental force, the weak force, quarks can actually change flavors too.
Now, back to protons and neutrons. They're each made up of 3 quarks. Well, 3 valence quarks to be exact.
Mathematically, there can be countless numbers of quarks at any time, but they don't really like to stick around. Though it's a complex world, understanding the building blocks that form a basis for everything that we know is super important for gaining insight into other STEM fields and even into the history of our universe. With so many unexplored paths, quarks might soon be used in quantum computing, or even to create new materials.
With the relatively young and ever-evolving nature of this field, who knows what could be discovered next, and by who?
Could it be you?
As Professor Einstein once said, if we knew what we were doing, it wouldn't be called research.
Stay quirky, my friends.